Hello friends, this is Dharmin Patel. Welcome to the lecture series of Mathematics-2. In this lecture, we will discuss the power series solution about regular singular point by Frobenius series method part 2. In the first part, we discussed about regular singular point by Frobenius series method case number 1, in which our initial roots are not differ by an integer. Now we are discussing about the case number 2 of Frobenius series method. In the case number 2, our initial roots are equal, and how to find the power series solution about our regular singular point. First of all, we recall the last lecture power series solution about the regular singular point. Y double dash plus pxy dash plus qxy equal to 0 be a second order homogeneous linear differential equation. A point x0 is said to be an ordinary point of our differential equation y double dash plus pxy dash plus qxy equal to 0 if limit x tends to x0 px and limit x tends to x0 qx both are exist. If one of the limit is not exist, then we can say that x0 be a singular point. If limit x tends to x0, x minus x0 into px and limit x tends to x0, x minus x0 qx whole square both are exist, then x0 is called regular singular point. In this case, we can apply the Frobenius series method. If one of the limit x tends to x0, x minus x0 px or limit x tends to x0 whole square qx is not exist at x0, then x0 is called the irregular singular point. In this case, we can't apply the Frobenius series method. Let us see the second case of Frobenius series method. As we know that x0 be a regular singular point, therefore limit x tends to x0, x minus x0 px and x tends to x0, x minus x0 whole square qx both are exist. 0 x minus x0 px equal to p0 and limit x tends to x0, x minus x0 whole square qx equal to q0. Now using p0 and q0, we can also find the initial equation r into r minus 1 plus p0 r plus q0 equal to 0, which is also obtained by putting minimum value of n during the calculation of example. By factorizing the initial equation, we get the initial roots r1 and r2. If the r1 and r2 are equal, then we have a case number 2 of Frobenius series method. Now our r1 and r2 are equal, that means initial roots are equal, then we can find the one solution of our differential equation, which is y1 equal to sigma n equal to 0 to infinity an x minus x0 raised to n plus r1. In this case, we can find the second linearly independent solution as y2 equal to del y by del r and put r equal to r1. Here we are differentiating partially y with respect to r and then put the initial root r equal to r1. Now we can find the general solution y equal to c1y1 plus c2y2, where c1 and c2 are arbitrary constant. Here y1 is depends on r1 and y2 is obtained by partial derivative of y with respect to r and put r equal to r1 in that partial derivative. Let us see one example of case number 2. Here our example is x into x minus 1 y double dash plus 3x minus 1 y dash plus y equal to 0. We have to find the power series solution about x0 equal to 0. First of all, we will check the x0 is singular or ordinary point. Here we will follow these steps. Here our differential equation divided by x into x minus 1, then we get px equal to 3x minus 1 upon x into x minus 1 and qx equal to 1 upon x into x minus 1. Now x0 and 0 both are singular point, but here we are discussing about the only x0 equal to 0 point, because we have to find the power series solution about only x0 equal to 0 point. Now we will check the x0 be a regular singular point or not. Let us see by calculation. Here x0 equal to 0 be a singular point of our differential equation. Now limit x tends to x0, x minus x0 into px, that is equal to limit x tends to 0, x px is 3x minus 1 upon x into x minus 1, x cancel, then we get finally minus 1 upon minus 1, which is equal to 1. So we have a p0 is exist. That means now limit x tends to x0, x minus x0 square into qx, that is equal to limit x tends to x0, x square into 1 upon x into x minus 1, x cancel, then finally after putting the limit we get 0, which is our q0, and it is also exist. Now we can say that x0 equal to 0 be a regular singular point of our differential equation. So we can apply the Frobenius series method for x0 equal to 0 point. So we take y equal to sigma n equal to 0 to infinity an x raised to n plus r with a0 not equal to 0, which is our power series solution about regular singular point x0 equal to 0. Now y dash is sigma n equal to 0 to infinity n plus r an x raised to n plus r minus 1, and y double dash equal to sigma n equal to 0 to infinity n plus r minus 1 into n plus r an x raised to n plus r minus 2. Now we will put y dash and y double dash in our differential equation, and our differential equation can be written as x square y double dash minus x y double dash plus 3x y dash minus y dash plus y equal to 0. Now after putting the value of y dash and y double dash in the differential equation, we get x square into sigma n equal to 0 to infinity n plus r minus 1 into n plus r an x raised to n plus r minus 2 minus x into sigma n equal to 0 to infinity n plus r minus 1 into n plus r an x raised to n plus r minus 2 plus 3x into sigma n equal to 0 to infinity n plus r an x raised to n plus r minus 1 minus sigma n equal to 0 to infinity n plus r an x raised to n plus r minus 1 plus sigma n equal to 0 to infinity an x raised to n plus r equal to 0. After multiplying the coefficient x square, x and 3x inside the summation, we get the sigma n equal to 0 to infinity x n plus r minus 1 n plus r an x raised to n plus r minus sigma n equal to 0 to infinity n plus r minus 1 into n plus r an x raised to n plus r minus 1 sigma n equal to 0 to infinity 3 n plus r an x raised to n plus r minus sigma n equal to 0 to infinity n plus r an x raised to n plus r minus 1 plus sigma n equal to 0 to infinity x an x raised to n plus r equal to 0. In the second and fourth summation, we have a power of x is n plus r minus 1. Now in the next step, we have to convert each power of x in x raised to n plus r. So we replace n by n plus 1 in the second and fourth summation. Then we get finally sigma n equal to 0 to infinity n plus r minus 1 into n plus r an x raised to n plus r minus sigma n equal to minus 1 to infinity n plus r into n plus r plus 1 an x raised to n plus r plus sigma n equal to 0 to infinity 3 n plus r an x raised to n plus r minus sigma n equal to minus 1 to infinity n plus r plus 1 an plus 1 x raised to n plus r plus sigma n equal to 0 to infinity an x raised to n plus r equal to 0. Now after putting the minimum value of n, we get the initial roots. Here we will put the minimum value of n, which is n equal to minus 1. We get minus r into r minus 1 minus r a0 x raised to r minus 1. And the remaining term will be c plus sigma n equal to 0 to infinity n plus r minus 1 into n plus r an minus n plus r plus 1 an plus 1 plus 3n plus r an minus n plus r plus 1 an plus 1 plus an into x raised to n plus r is common from every summation equal to 0. Now compare the coefficient of x raised to r minus 1 and x raised to n plus r with RHS equal to 0, which is our next step, and for n equal to minus 1 we get minus r into r minus 1 minus r a0 equal to 0. We have a a0 not equal to 0, therefore r square equal to 0. That implies we have a r1 equal to 0 and r2 equal to also 0. We have a initial equal roots. Now r1 and r2 are equal, so we have a case number 2 in Frobenius series method. Now for n greater than or equal to 0, after properly simplifying we get these steps, and then we get the finally n plus r plus 1 whole square an plus 1 equal to n plus r plus 1 whole square equal to n. Then after cancelling n plus r plus 1 whole square from both sides, we get the recurrence relation for n greater than or equal to 0, which is an plus 1 equal to an, which is the recurrence relation for r1 equal to r2 equal to 0. Now we get the first solution by putting r1 equal to 0 in our recurrence relation. Then finally we get our recurrence relation is an plus 1 equal to an for all n greater than or equal to 0. Now y1 equal to x raised to r1 into a0 plus a1x plus a2x square up to so on, which is the power series solution for r1 equal to 0. Now putting the n equal to 1, 2, 3 in our recurrence relation, we get a1 equal to a0, a2 equal to a1 equal to a0, a3 equal to a2 equal to a1 equal to a0. That means we have a an equal to a0 for all n. Now putting this value in our power series solution, we get the y1 equal to a0 into x raised to 0 into 1 plus x square plus x cube up to so on. Here 1 plus x square plus x cube be a power series solution of our differential equation. Here 1 plus x square plus x cube be a Maclaurin series of function 1 upon 1 minus x. Then we get the first solution is a0 into 1 upon 1 minus x, where a0 be an arbitrary constant. Now we will find the second solution in case number 2. Here y2 is obtained by del y by del r and put the r equal to r1, which is 0. After taking the partial derivative of a0 into x raised to r upon 1 minus x with respect to r, we get a0 into x raised to r log x upon 1 minus x. Now we will put the r equal to r0 in this partial derivative. Then finally we get the second solution a0 into x raised to 0 log x upon 1 minus x. That means we have a a0 into log x upon 1 minus x, which is our second linearly independent solution. Then finally y2 equal to a0 log x upon 1 minus log x. Here capital A0 is an arbitrary constant. Now we have a final solution in step number 7, which is y equal to c1y1 plus c2y2, where y1 is equal to a0 into 1 upon 1 minus x and y2 equal to capital A0 log x upon 1 minus x, where c1 and c2 are arbitrary constant. So this is the second case of Frobenius series method. In this case we studied how to find the power series solution about regular singular point when our initial roots are equal. Thank you very much.